we've considered a pendulum that's swung out some distance or to some angle theta, and we want to find how much higher it is out here than it is here. Now that's something that's fairly easy to demonstrate. I can make a pendulum. Excuse me, I'm fumbling with a hook here. I'll just fumble with a bigger hook. There's a little one isn't going to cooperate. Okay. Here's a pendulum. Okay? This is hanging here. If I swing this thing out, we see that it goes higher along the arc of a circle, somewhat like the circle that I've drawn here. And we're trying to determine how much higher it goes. Now I've exaggerated this distance here, and actually I think this distance is a little bigger than this distance in my picture. But what we're trying to find is this distance. How much higher is the pendulum here than it is here? To solve this problem, and you should again try to solve the problem before you look at my solution. If we have angle theta here, then if L is the length of the pendulum, that's here or here, then this distance here, which, let's note, if we can find this distance, which is the side of a right triangle with known angle and hypotenuse, so we can certainly find this distance. If we can find this distance, then we can find this distance by subtracting this distance from L. Okay, so in any case, if L is the hypotenuse, then this distance is L times the cosine of theta, isn't it? Because this is the side adjacent to the angle, this is the side opposite. This side will be L times the sine of theta. This side will be L times the cosine of theta. So we can see that the cosine of theta is distance over L. Distance is L times the cosine of theta. And from that it follows that the distance we're trying to get, which I haven't written down here, is going to be L, this distance, minus this distance, which is L cosine theta, so that this distance is going to be L minus L cosine theta. So let's write that in. Okay, so that's L minus L cosine theta, or L times 1 minus cosine theta if we factor out the L. Excuse the angle at which I've written this, but it's about the only angle from which I can write here and be legible. In class, we experimented a little bit. We took a pendulum hanging from the ceiling. There's a pendulum conveniently hanging. This is a physics lab. That was 118 centimeters from the ceiling down to the middle of the pendulum. We then displaced the pendulum 30 centimeters in this direction and estimated this altitude. Now the estimate that was suggested in class and the one that we followed was, well, it looks like the tangent of the angle is 30 centimeters over 118 centimeters. Turns out that's not really true, and we'll see why in a minute, but we went ahead and used that anyhow because it's for the small angle that we used, it's not going to be a bad approximation, and you'll see in a minute why we can get, how we can get a better approximation. So, if the angle theta, that is the angle up here, if the angle theta is the inverse tangent of 30 over 118 or 14.2 degrees, then we have the following situation. We have the 118 centimeters that the pendulum hangs, and I haven't indicated that whole distance, but that's the distance down to here. We have the 118 centimeter hypotenuse of this triangle, and we have an angle of 14.2 degrees here. From that, it follows that this side of the triangle should be about 114.4 degrees, and that this distance, this small distance here, which is how much higher the pendulum is at this point than it is at this point, this tiny little distance in here should be 118 centimeters, the whole distance, minus the 114.4 centimeters down to here, or 3.6 centimeters. Measuring the pendulum from tabletop up to the pendulum, we found that the pendulum was 3.7 centimeters higher here than here, which agrees real well with our 3.6 centimeters. As a matter of fact, it's entirely possible that the table wasn't completely level and that the table was off by a millimeter. In any case, we got a very good comparison and very good results here.